Hello, everybody, and welcome back to your channel of Math and Engineering Made Easy. In the last session, we were working on exponents. We looked at the laws of exponents, and we had a few examples. Of course, at school, you will get more examples, but hopefully you understand now how to deal with those. Today, I'm going to look at the inverse operation. You already know a lot of inverse operations and operators that you even may not think of them as that. For example, addition and subtraction are inverse operations. If you have a number and you add 10 to it, to return back to the number, you subtract the 10. Whatever you added, you subtract, right? Whatever you multiply, you divide. So multiplication and division are inverse operations. Square and square root, or any power like the cubic root and cube, are inverse operations. There are so logarithm, which we are going to talk about today, is the inverse of the exponents that we talked about last time. In fact, when I go through the laws of logarithm, they would resemble it. It gives you an idea about what we did last time. There is some kind of resemblance, of course, because it's the inverse operation. Also, the reciprocal, 1 over x, is the reciprocal of itself, meaning if you do it twice, you go back and get the x. So you divide 1 by x, and then you divide 1 by x, you get x, right? So there are some like that, and there are too many inverse operations that you will learn about probably in Calc 2. I'm sorry, Algebra 2, I believe. So what is logarithm? For example, we can write, I'm going to write, say, log to the base 3 of a number, let's make it 243 equals 5. You say, wait, I don't understand. Where did you get these numbers from? Okay. Bear with me for a second. This is the base. Remember what we call the base in the exponents? And that is the exponent or the power. So basically what he's saying is 3 to the power of 5, meaning 3 times 3 times 3 times 3 times 3 is 243. Okay? So that's the opposite of that, the inverse of that. I had a 3 and I say, if I raise it to the power of 5, I get 243. And then I ask you, what power did I raise the 3 for to get 243? Because I want to go back to 3. Okay, so you take the log of that. Okay? The log can have any base, as you know, right? So I can make, if 2 to the 6 is 64, then log of 2 of 6, log to the base 2 of 64 is 6, and so on and so forth. So you can pick any number, really. Except that if the base equals 10, we don't write it. We don't write the 10. So we don't say log to the base 10. Doesn't make sense. Because originally, logs had base 10. That was common to use because we use a decimal system. So we have 10 digits. And it was easy when you tell me 100, I say, oh, log 100 is 2 because 10 squared. 1,000 is 3, a million is 6, a billion is 9. It's easy. It's easy only if it's a power of 10. But if it's, what is the log of 50? I don't know. I have to do it through, we had tables to use because we didn't have calculators. And when we didn't have calculator, there was like tables of logarithm that help us make the power multiplication. Power multiplication, that's what we did last time, right? When we had 2 to the 3 everything to the 4, it's like 2 to the 3 times 4. So that power became multiplication. In the logarithm, it's something similar. Well, if I had to multiply two numbers and it's a long multiplication, instead of doing it, I can transform it into an addition problem in logarithm and then use the inverse also as in tables to find the answer. Life was tough, right? We didn't have calculators, and so we had to deal with these. Square or a root would be division. Remember, we talked about that in powers. So it's very similar. Not exactly. Here I'm going to, so that I don't confuse you, I'm not going to write any base. So I'm going to write genetic laws. It work for any base. I can say log to the base b, but just for simplicity, I'm going to say log of a times b equals log of a plus log of b. Wait, I had something similar, but maybe backwards with the exponents, right? I had x to the a times x to the b equals x to the a plus b. So there were two things multiplied. They transformed into two things added. Log a divided by b equals log of a minus log of b. We had something similar, not exact, of course. These are the inverse of each other. We had x to the a divided by x to the b equals x to the a minus b. Also, if we have log of a to the power of b, it becomes b times the log of a. Remember when we had x to the a to the b, it became x to the a times b. Of course, they are not the same, but you see that exponent, power, multiplication, power, multiplication. Also, if I have, like, what should we do? Like, let's say log of the square root of a. I don't think you will get something like that, but it becomes 1/2 log of a. Wait, what is the square? So x to the a, and I take the square root. Oh, here I take the square root. I should have said b and that b. I don't have to make it just for square root. So let's make that b and that b. We said x to the a, if I take the bth root of that, remember? We said that was x to the a divided by b. So really, we have some kind of similarities, right? Not identical, but we see multiplication became addition, division became subtraction, power became multiplication, and root become division. Excuse me. We say that log to any base of 1 equals 0. And we said x to the 0 equals 1. Log of a number, let's say a number b, and the base was b, is 1. Here we say x to the 1 is x. Of course, that's not. Log of 1 over b is negative log of b. And here we said 1 over x to the a equal x to the negative a. So the rules have some kind of similarity. Unfortunately, I see it a lot that people would have log A plus B, they make it log A times log B, which is not correct. No, the multiplication is simplified. So think about the log simplifies thing. So if they were addition, I cannot simplify the addition. I can combine them into multiplication, but I don't simplify the addition or the subtraction. Okay? So anyway, this is a generic thing. Let's take some examples. Suppose I say, what is log to the base, say, 7 of 343? Well, if I give you something like that, you have to suspect that 333 is a power of 7. So you say 7 is 7 to the first, right? No, 7 doesn't equal 343. If I square it, so I take it to the power of 2, I get 49. No, 49 is not. So you use your calculator and get 7 cubed. You say that you find that 7 to the third power is 343. So the answer here is 3. Meaning, notice that this is log to the base 7 of 7 cubed. This is a power. The power becomes multiplication. So that should be 3 times log of base 7 of 7. But log of b to the base b is 1. So log of 7 to the base 7 is 1 because 7 to the first power equals 7. So this thing is 1, so the answer would be 3. Okay? Now, let's take some other examples. For example, what if I say, find the log, say, to the base 5 of 25 times 25? Well, I know that 25 is 5 squared. So I'm going to write it as log to the base 5 of 5 squared times 5 squared, or 5 to the fourth power. Very similar to that. When I have 5 to the fourth power, the 4 becomes a multiplier, and log 5 of 5 is 1, so I get 4. Meaning, if I raise 5 to the fourth power, I should get 25 times 25. Of course, 5 squared is 25, and 5 squared is 25. So 5 to the 4 is 25 times 25, or 625. Okay, something else. But as we will see next time, when we take some equations and try to solve for a variable, say x, using logarithms or using exponents, we have some work to do. So let's assume here, I'm going to say, let me think of something I want to do. What if I want you to find log to any base, let's make it base 4, of something that is not a power of 4? Like, whatever, 33. Meaning, I'm telling you, there is some number that if you raise 4 to that power, you get 33. I know that 4 squared is 16, 4 cubed is 64. So it's something between 2 and 3. But how do I find it? Your calculator can't help you because the calculator has log. Do you see the log? That's base 10. And there is the len, which is base E. But it doesn't give me all the bases in the world because I can make base of 2.1, for example. How can the calculator give me any base? It turns out that there is a very important simplification that I'm going to write here. We will need it next session. Log to any base b of any number a can be written as log to the base 10 of a divided by log to the base 10 of b, of the base. I have a log here, so I can solve it. And this also is a natural log of a over natural log of b. Let's try it. I want to find log to the base 4 of 33, but I don't know how to do it. So I'm going to say, oops, what is len 11? Did I click on this? 33 divided by log of 4 equals 2.522197. Of course, if you 2 or 3 decimal places are enough. I'm just writing what's here. So if I take 4 and raise it to this power, I get 33. Of course, this is the approximation. How about the natural log? So if I say natural log of 33 divided by natural log of 4, yeah, absolutely, I get the same result. And this is a very powerful law because it can help you when you have different logs. Finally, if I come now and tell you what is log of 33 but to the base 2? What do you think that would be? You know that 4 is 2 square, right? So that becomes 2, that's because it's 2 square is 4, times log to the base 4 of 33. Remember last time when we were talking about exponents, and I tell you sometimes they tell you simplify 2 exponents, but the bases are not the same? You always have to understand whenever they ask you this question, it means that these bases, one of them is a power of the other. Same thing with the log. If they give me log to the base 2 and ask me what is the log to the base 4, I will divide this by 2. Or if they want it to the base 8, I will divide this by 3 because 2 to the third is 8. And so on and so forth. Let's see. Let's see. So that should tell me if I multiply this answer by 2, I'm getting 5.044. Is that true? We don't know. So let's try either log 33 over log 2 or natural log of 33 over natural log of 2. It doesn't matter. Log 33 divided by log 2, 5.044, which is twice as the log to the base 4. So that's similar to what we did there when the bases were not the same, but one base, for example, was 5 and the other was 25, or one was 3 and the other was 27, 3 times, like power of 3, and so on and so forth. So log problems, you will see, for example, they tell you to simplify, and I just don't want to, I should have prepared something for you. So let's say they say log to the base 3 of x squared so let's say plus log to the base 3 of 4 minus log to the base 3 of 2x minus 4, whatever. I know that when I add two things, It means I'm multiplying. You see, I go from right to left. So these two would be log to the base 3 of x squared times 4, 4x squared. And then when I have minus, that means I'm dividing. So you see what I did? I can do those in one step. I say plus, meaning I'm going to multiply 4 by x squared. Minus, meaning I'm going to divide. So let's write it on two steps. So the second step is that. The third step would be log to the base 3 of 4x squared over 2x minus 4. And that is the simplification, or not the simplification. Here I combined everything into a single log. And maybe one of them was log to the base 9. So I'm going to say, oh, 9 is 3 squared. So I'm going to take that and divide it by 2. The 2 would go up and becomes 8x squared. So you see what I'm saying? It's like you have to transform all of them to the same base and then do that. And let's say you have this equation equals 3.5. So they told you in the beginning, all of this equals 3.5. So I combine these three logs into one log that has a ratio. And then I would say, okay, so 3 to the 3.5 equals 4. Of course, these numbers are, ridiculous, right? They're not easy. So let's make that 2. Let's say that we give you, I just making that on the run. So 3 squared or 9 equals 4x squared over 2x minus 4, right? Because now I said base to the power of the right-hand side equals whatever I have. Right? That's what we said here. 3 to the 5th equals that. 3 to the 2nd equals that. And then you say 4x squared equals 9 times that minus 36. So 4x squared minus, we'll do that next time because next time we are going to do equations, but I was giving you just heads up. And then that equals 0, you divide by 2, so you get 2x squared minus 9x plus 18. Of course, I made some numbers, so this basically will be complex root. Okay, so you won't get a number that makes sense to you. So just forget it. It's just I came up with the equation and then some other person can solve this equation. You would learn how to do it. Or if you already learn how to solve quadratic equations, you can use the quadratic formula and get negative b plus or minus square root of b squared minus 4ac over twice a and get two complex roots. Okay, so this was just an introduction. I want you to go back over these laws and be careful. I see that a lot of times some people would say log a minus log b, and then they say it's log a divided by log b. So how did you transform this difference of two logs into a ratio of two logs? You change the problem. You have to say, oh, it's log a over b. Yeah, that's fine. But you cannot change the plus into times. You don't say log a plus log b equals log a times log b. It's as if you are saying 2 plus 4 equals 2 times 4. No, you cannot do that. So be careful with this pitfall. And it's not hard because if it's already addition or subtraction, you cannot simplify it anymore. Yes, you can combine them. And the division would be inside the log, not outside. Not log a over log b. No, it's log a over b or log a times b. Okay. And we said we call this number the base. If I don't write it, I mean 10. But instead of keep writing B, 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 and then I have to use another letter. So I say A times C and log A plus log C. It may be confusing. So I said, okay, ignore that. And you can have any number here in the base. And these laws will stay the same. Okay? I hope it wasn't confusing. I know these two things are like inverse of each other. So like sometimes it's confusing, but next time we'll see how we use them in conjunction to solve equations like exponential equations or logarithmic equation. Thank you for your time. If you have any questions, leave me a note in the comment section, and I will get back to you as soon as I can. Thank you very much and hope to see you soon.